We have been learning about calculating magnetic field and have done some problems based on that. Now, I want to focus on vector potential for magnetic field and do one problem related to that in this lecture. And the other thing I want to talk about is boundary conditions on magnetic fields. Although we will not be using them very soon, but it is important to derive them right now by looking at the structure or the equation satisfied by magnetic fields. So, these are the two things that I will be focusing on in this lecture. To start with, let us look at the vector potential. We had done one or two problems based on this when I introduced vector potential to you, and the vector potential is related to the magnetic field by this relationship. That magnetic field is given by curl of A. And where does this come from? This arises because the divergence of the magnetic field is 0, and therefore, B can be expressed as the curl of a vector potential. Furthermore, A is not unique. Given an A, I can equally well get the same magnetic field B by A plus some gradient of some other function chi, because divergence of or the curl of gradient is always 0, and therefore, B does not change even if I add to A gradient of some function. And then we had calculated A for some one or two current distributions. In this lecture, I want to start by introducing you to this problem from Griffiths. So, this is an example in Griffiths. Griffiths' book, and from chapter 5 on magnetostatics. He solves it, and the problem is this: given a spherical shell carrying uniform surface charge density sigma is rotating about the z axis with angular speed omega. So, what I want you to calculate is number 1, calculate the surface current density. Okay. And second, calculate the vector potential for this problem. And once you calculate the vector potential B, you can easily calculate its curl of A. So, what I would like you to do is read this example in chapter 5 of the book. I think it's example 11. And to perform the integral here, he again rotates the axis in a certain way, so that the point of observation is on the z axis. So, while reading this example, I would like you to go back to understand this calculation. Go back to our calculation of electrostatic field, electrostatic potential for sigma equals sigma naught cosine theta. This I did in the first week in the second or third lecture. So, go back and see how we perform that calculation by rotating the axis and bringing the point of observation on the z axis. Exactly same thing is done here. So, if you go back there or go through that solved problem again, you will be able to understand the solution here much easily. So, then I am leaving that for you as an exercise. The problem I want to do now, just to get your attention to and get you sensitive to the vector potential, is this. This is problem number 24 from Griffiths, chapter magnetostatics. What you are given is, if the vector potential somewhere is given as k phi, find the current density for this vector potential. Why I am doing this problem is somehow you may feel that, look, I mean, A is in phi direction, there is a unit vector given in phi direction. So, if I calculate del square A, which is supposed to be minus mu 0 j, it may come out to be 0, but this is incorrect. I have to be a little more careful, and that is why I am doing this problem. And I can do the calculation in cylindrical coordinates. I'll use cylindrical coordinates. You see, del square A is not 0 because phi is not a constant unit vector. Rather, it depends on phi. So, phi is minus sin phi x plus cosine phi y, and x and y are constant unit vectors. X and y are constant unit vectors. So, now I can do the Laplacian calculation. So, I am calculating del square A, which is equal to del square of k sin phi with a minus sign x plus k cosine phi the y. And I need to use the expression for del square in cylindrical coordinates, which is 1 over s partial s of s partial s plus 1 over s square double derivative double partial with respect to phi plus double derivative with respect to z. Since both the quantities here, which I am encircling with green, depend only on phi, the terms d by dz square, this is 2, and d by ds are not going to contribute. So, what I am going to get del square A as k over s square x d2 by d phi square of sin phi, there is a minus sign here, plus y d2 by d phi square cosine phi. And that is a very easy calculation to do, and that comes out to be del square A comes out to be k over s square. Second derivative of sine and cosine functions are negative of that. So, this will come out to be x sine of phi minus y cosine of phi, which is minus k over s square phi, and this is equal to mu naught j. with a minus sign. This gives me the answer. J r is nothing but k over mu naught s square in the phi direction. That is the answer. So, I did this problem, which is a very simple straightforward problem, but you should not fall into the trap that given phi unit vector that everything is 0. You have to be careful. So, just to kind of give you a feel for the vector potential, what I am going to discuss the next is the boundary conditions. On magnetic field B. It is a good time to do it here, because you are kind of getting familiar with the maths involved in magnetic fields, but we will be using it later. So, when do the boundary conditions arise? Suppose I am given a boundary, a surface. So, here is the surface, and there is B field below it. So, let us write it B lower, and there is B field above it. Or even better word would be B under the surface and B above the surface. Vector. How can I relate the B or its components above and below, or under the surface and above the surface, or even under is better, B below the surface and above the surface. So, how can I relate the components of B above the surface and below the surface? And that is what we want to do now. Just like electric field satisfies those boundary conditions on a surface, so does magnetic field. But it is a slightly more subtle concept here mathematically and to visualize it. So, here is the surface. I am now making it one dimensional, and here is B below, and here is B above. Let us first concentrate on the perpendicular component of the field. For this, I will consider a small box on the surface, very small radius. Then I have divergence of B dV over this box equal to 0, and this will be equal to B perpendicular above times the area minus B perpendicular below times the area, and some contribution from the sides. So, let us now look at this box. I said it is very thin, so that we can concentrate only on the field near that point where the box is made, right. It hardly changes, and I am also going to make this box very flat. That means the thickness is almost 0. So, this implies the contribution from the sides is 0, and therefore, I get B perpendicular above is equal to B perpendicular below. That is one boundary condition. So, perpendicular component remains continuous. Recall that in electric field, it is the perpendicular component that changes discontinuously because of the surface charge. Here, the perpendicular component of B remains continuous, again because of the divergence theorem. In E also, it was the divergence theorem that gave the discontinuity in the perpendicular component. Now, I want to focus on the parallel component. Again, let us look at the surface, and locally where I am looking, let us say the direction I am right now taking is this direction to be the x direction. There is some B field. There is some B field here, B below and B above. We have already established that the perpendicular component is continuous, and let me take the direction going up as y, and y is also the normal to the boundary surface. Okay, I am showing everything to be big, but these are supposed to be really small. And now I am going to take to consider parallel component a small loop here. Notice that the z axis is coming out. Now, by Stokes' theorem, I have curl of B dot ds is equal to integration B dot dl, and I am going to apply it to this loop. Curl B is nothing but j mu naught j r. So, I have mu naught j r dot ds integral is equal to B x above minus B x below times dl, because dl is in x direction. And again, if I take this loop to be thin enough, the side contributions are going to be 0, which I am neglecting. So, what do I have now? I have taken the surface, direction going to the right as x, normal to the surface is y, z axis is coming out. I have taken a loop, the width is almost negligible, perpendicular to the z axis. Z axis is coming out, right, and then I got that mu naught j dot ds is equal to B above in the x direction minus B below in the x direction times dl. This is integral. Now, ds I can write as dl times dw, and dw is going to really 0, much faster than dl. In fact, the whole thing shrinks. So, it is just on the surface. So, unless J contains a delta function, Dirac delta function actually, in W, integration j dl dw is going to be 0. So, if there is no surface current, what is surface current? It is flowing on the surface. If there is no surface current, then B above x is equal to B below x. So, x component will be parallel. Otherwise, I am going to have integration mu 0 j dot ds is not 0 if there is a surface current, and if surface current is there, then j R can be written as some k vector delta w. So, delta w then on integration over w will go away, and I will have then mu 0 j dot ds is equal to mu 0 integration k dot ds. You can see from the way I made it is in the minus z direction dl, which I can write as minus mu 0 k z dl. So, what do I get? I get b above x minus b below in the x direction is parallel to the surface is equal to minus mu 0 k z, because dl will cancel. Now, let us see, k is a surface current. This vector is going to be k x x plus k z in the z direction. Let us see what have we got. I will just recap again. Y is going up, x is coming to the right, z is coming out. We have taken this thin loop going around, and we have found that b above x component minus b below x component is equal to minus mu naught k z. K is equal to k x x minus plus k z z. I want to write this in the vector form, and I will do it in a minute. In exactly the same manner, I can now take z going to the right, x then will be going in, and y will be going up. And again I can take that loop, do my integration, and go through the entire process, and what I am going to get is b above z component minus b below z component is going to be equal to mu naught k x. I can now combine the two and write it very nicely. So, I can write the two together as b above vector parallel to the surface minus b below parallel to the surface is equal to minus mu 0 k z x plus mu 0 k x z, which I can write as mu 0 k x x plus k y y, k y, so there is no k y, so I will cut it, which I can write as mu 0 k x x plus k z z cross y. Y is normal to the surface, and therefore, I can combine everything and write that b above parallel minus b below parallel is equal to mu 0 surface current cross n, where n is normal unit vector going from obviously below to above on the surface. So, we derived the second condition also. So, let me now quickly summarize this lecture by saying that 1, we have worked a bit on the vector potential problem, and on this I have left example 11, chapter on magnetostatics in Griffiths for you to read, and you will get help from VR calculation for surface charge density sigma naught cosine theta. And 2, we have derived boundary conditions on magnetic field, and that gives me that B perpendicular is continuous. That means B perpendicular above the surface is B perpendicular below the surface, and B parallel above minus B parallel below is mu 0, the surface current across n. N is from below to above. If there is no surface current, then B is continuous. So, B parallel is continuous if there is no surface current. Thank you.